Hello there. Right now, as you settle into stillness, there's a sound moving through space that's older than mountains, older than oceans, older than the sun itself. It's been traveling for so long that entire galaxies have lived and died while it journeyed toward us. This isn't science fiction, it's real. A vibration from the very beginning of everything, stretched across the entire universe, waiting 14 billion years just to reach your ears. And the strangest part, we can actually hear it now. Before we dive deeper into this ancient mystery, if stories like this help you feel calm or spark your curiosity about the universe, hit that like button and subscribe so you don't miss tomorrow's journey through the cosmos. Also, drop a comment telling me where you're listening from and what time it is there right now. There's something beautiful about knowing we're all under the same vast sky, separated by distance, but connected by wonder. Now, let yourself sink deeper into comfort as we begin. Tonight, we're going somewhere extraordinary. We're heading to the edge of everything we can detect, to a moment when the universe was young and wild, to capture something almost impossible. A sound, not just any sound, but the deepest note ever played, stretched across billions of light years, carrying secrets from before Earth existed. Space is often called the silent void, and in a way, that's true. There's no air up there, nothing for sound to push through the way it does here on Earth. But silence and emptiness aren't quite the same thing. Between the stars, in the vast darkness, there are whispers, vibrations so low, so stretched out by time and distance, that they don't sound like anything we'd recognize as noise. Yet they're there, humming through the fabric of everything. The sound we're chasing tonight is special. It's the oldest sound possible, a vibration that began when the universe itself was born, when everything we know was compressed into something smaller than a grain of sand. That moment, that beginning, sent ripples through space that are still traveling today, still moving, still carrying their ancient message. Think about that for a second. Every breath you take, every heartbeat, happens in a universe that's still ringing from its first moment. Like dropping a stone into a pond and watching the ripples spread, except the pond is all of space, and the stone was the birth of time itself. Those ripples are still spreading, still moving outward, and we've learned how to listen to them. This isn't just about sound, though. It's about connection. These vibrations from long ago helped shape where galaxies would form, where stars would ignite, where planets would gather around those stars. In a very real way, this ancient cosmic hum had a hand in creating the world you're living on right now. The chair you're sitting in, the air you're breathing, the elements in your body all came from a chain of events that started with these primordial ripples. So, how do we hear something that's 14 billion years old? How do we capture vibrations from before Earth existed? Before our sun was born? Before any of the stars you can see in tonight's sky were even a possibility? That's where the story gets really interesting. But to understand how we found this ancient sound, we first need to understand what sound actually is. And that journey begins with something much simpler, much closer to home. It begins with understanding the nature of vibration itself, and why sound needs something to travel through. Which leads us to a question that changes everything. Before we can hear the universe, we need to understand what sound actually is. And it's simpler than you might think. Sound is just things bumping into each other. That's it. One thing pushes another, which pushes another, and on in a chain reaction of tiny collisions. Picture dropping a stone into a still pond. The stone hits the water and pushes it down. That pushed water has to go somewhere, so it shoves the water next to it. That water pushes the next bit, and the next, creating ripples that spread outward in circles. Sound works exactly the same way, except instead of water, it's usually air doing the pushing. When you speak, your vocal cords vibrate. They push against air molecules, squeezing them together. Those squeezed molecules bump into the ones next to them, which bump into the next ones, creating a wave of pressure that travels outward. When that wave reaches someone's ear, it pushes on their eardrum, and their brain translates those pushes into words. Everything you've ever heard is just air molecules doing a domino effect against your eardrum. Here's the key part, the thing that matters for our cosmic story. Sound needs something to travel through. It needs molecules or particles or atoms, something physical that can push and be pushed. Without that, sound can't exist. You can't have a wave if there's nothing to wave. This is why sound travels differently through different materials. In water, sound moves faster than in air because water molecules are packed tighter together. They don't have as far to travel before they bump into the next molecule. In solid steel, sound travels even faster, about 15 times faster than through air. The tighter things are packed, the quicker the push can spread. But what happens when things aren't packed tight at all? What happens when there's almost nothing there? This is where space becomes interesting. Between Earth and the Moon, between planets, between stars, there's mostly nothing. We call it vacuum. And in a vacuum, there's nothing to push. No air molecules, no water, just emptiness. So, when movies show spaceships exploding with huge booms, that's not real. If you were floating in space and a spaceship exploded right next to you, you wouldn't hear a thing. The explosion would create light, heat, debris flying everywhere, but no sound. Because there's no air to carry the pressure wave, the vibration has nowhere to go. This is why space seems silent. And for a long time, scientists thought it was completely silent. Just an endless quiet void where sound couldn't exist at all. But they were wrong about that. Not completely wrong, but wrong enough that it matters. You see, space isn't actually empty. It's close to empty, incredibly close. But there are still some particles out there. Bits of hydrogen gas, tiny specks of dust. Atoms spread so thin that you might find just one or two in a space the size of a coffee cup. But they're there. And if particles are there, even just a few, then technically sound could travel. It would be incredibly faint, impossibly quiet, but possible. This realization changes everything. Because if sound can exist in space, even in the thinnest possible form, then maybe the universe has been making sounds all along. Maybe we just haven't been listening properly. Let's stay with this idea for a moment. Space seems silent, and in most ways, it is. If you were floating between Earth and Mars right now, you wouldn't hear anything. Not the sun burning, not meteors streaking past, not planets spinning on their axes. Complete silence would surround you. But that silence isn't the same as nothing. Think about the difference this way. An empty room is quiet, but it's full of air. Sound can travel through that room perfectly well. You just need something to make a noise first. Space is different. It's like a room where someone removed almost all the air, leaving just the tiniest traces behind. In a room like that, sound could technically exist, but it would be so weak, so faint, that you'd never hear it naturally. Between the stars, in the vast darkness, there are scattered hydrogen atoms. Not many. In fact, in the space between galaxies, you might find just one atom in an area the size of a beach ball. That's incredibly empty, but it's not nothing. And those lone atoms, spread across mind-bending distances, create a kind of medium. The thinnest possible medium, but a medium nonetheless. Now, here's where it gets interesting. Sound in space wouldn't sound like anything we know. It would be too low for human ears to detect. The wavelengths would stretch for thousands or millions of miles. One complete vibration might take years to finish. It would be less like a note and more like an impossibly slow pressure change moving through the cosmic nothing. But just because we can't hear it naturally doesn't mean it's not real. Just because something exists beyond our senses doesn't make it imaginary. Bats hear sounds too high for us. Elephants communicate with rumbles too low for our ears. Reality doesn't stop at the edge of what humans can naturally detect. Scientists started wondering about this decades ago. If space has some matter in it, even just traces, could pressure waves exist? Could vibrations travel through the thin cosmic fog? And if they could, what might be creating those vibrations? Surely something out there, in all that vastness, must be making waves. They found their answers in the most unlikely places. In the hot gas between galaxies. In the material swirling around black holes. In the plasma ejected from exploding stars. All of these create pressure waves, pushing through the thin cosmic medium, creating sounds that exist even though no one can hear them in the traditional sense. But these discoveries led to an even bigger question. If space can carry sound now, in its current thin state, what about when the universe was younger? What about when everything was packed much tighter? When there was no vast emptiness between things? What could sound have been like then? This question takes us backward through time, not just years or centuries, but billions of years. Back before Earth existed, before the sun was born, before any stars lit up the darkness. Back to a time when the universe looked completely different, when everything we can see today was crushed together into something impossibly small and impossibly hot. A time when sound didn't just exist, it dominated everything. We're going back now, way back, to a moment so early in time that numbers almost stop making sense. About 13.8 billion years ago, everything began. Not just Earth, or the Sun, or our galaxy. Everything. All the matter, all the energy, all the space itself. It all appeared in an instant that scientists call the Big Bang. But here's the thing. The Big Bang wasn't really a bang. It wasn't an explosion happening somewhere in space. It was space itself, appearing everywhere at once. Imagine trying to picture that. There was no outside, no place where it happened. It happened everywhere, because everywhere was being created at that exact moment. In the very first fraction of a second, the universe was smaller than the period at the end of this sentence. Everything that would eventually become billions of galaxies, each containing billions of stars, was compressed into something tinier than you can imagine. And it was hot. Not hot like fire, not hot like the center of the sun, hot in a way that would make the sun seem frozen by comparison. At that temperature, matter as we know it couldn't exist. Atoms couldn't form. Even the particles that make up atoms couldn't stay together. Everything was a thick soup of pure energy and fundamental particles, all squeezed impossibly tight. This wasn't empty space with a few scattered atoms like we have now. This was dense, solid, thick as concrete, but made of light and energy. And here's what matters for our story. In that thickness, in that density, sound could travel perfectly, better than through air, better than through water, better than through steel. The early universe was the ultimate medium for pressure waves. Every vibration, every ripple, every disturbance moved through it like music through a concert hall. As the universe began expanding, things started to cool. Not quickly, not like turning off a stove, but gradually, moment by moment, the temperature dropped from impossible to merely extreme. And as it cooled, particles started sticking together. First, the simplest particles. Then, after a few minutes, the first atomic nuclei. The universe was still too hot for full atoms, but the building blocks were forming. During this time, the universe was still incredibly thick. Thick enough that light couldn't travel freely. Photons, the particles of light, would try to move, but immediately bump into something else. It was like trying to see through fog, except the fog was made of the fundamental building blocks of matter. Nothing could see through it, but sound could move just fine. For the first 380,000 years of existence, the universe was like this. A hot, dense, opaque soup where sound waves traveled freely, creating patterns and rhythms that spread through everything. These weren't quiet vibrations. They were powerful pressure waves moving at incredible speeds, compressing and expanding the cosmic material in regular pulses. And then something changed. The universe had expanded enough and cooled enough that atoms could finally form completely. Electrons settled into orbit around nuclei. And when that happened, light could suddenly travel freely for the first time. The universe became transparent. But in that same moment, the medium for sound started to thin out dramatically, setting the stage for those ancient vibrations to transform into something we could eventually detect. In that dense early universe, something remarkable was happening. The cosmic soup wasn't perfectly smooth. There were tiny variations in density. Some regions had slightly more matter than others, and these differences created pressure. Where there was more matter, gravity pulled things inward. Where there was less, the intense heat and pressure pushed outward. This push and pull created waves, sound waves, the first sounds in existence. These weren't sounds you could hear, even if you had been there. They were far too low in pitch. One complete wave might stretch across thousands of light years in the early universe. But they were real vibrations, moving through the thick cosmic material at tremendous speeds. About half the speed of light, actually. Nothing moved slowly back then. Picture the entire universe ringing like a struck bell. Except instead of metal vibrating, it was space itself, filled with this dense mixture of matter and energy, all pulsing with regular waves of compression and expansion. Some regions were being squeezed tighter, others were spreading out, and this pattern repeated over and over in a cosmic rhythm. The waves moved in all directions at once. There was no up or down, no left or right, just outward, in every direction simultaneously, creating a three-dimensional pattern of ripples spreading through everything. Like dropping a stone in a pond, but the pond extends in every direction you can imagine, and the ripples move through depth as well as across the surface. Different frequencies existed at the same time. Some waves were longer, stretching across vast distances. Others were shorter, creating tighter patterns. All of them traveled together, overlapping and interfering with each other, creating complex patterns that wove through the fabric of the young universe. It was a symphony, but played in frequencies no ear would ever naturally hear. These vibrations weren't gentle, they were powerful. Wherever the wave compressed matter, the density would increase dramatically. Then, the pressure would build and push back, creating the expansion phase. Then, compression again, over and over, like a cosmic heartbeat, pulsing through everything that existed. The fascinating part is that these sound waves weren't just noise. They were shaping the future. Where the waves compressed matter repeatedly, those regions would eventually have more material to work with. Where the waves spread things out, those areas would end up less dense. This pattern would later determine where galaxies formed, where clusters of galaxies gathered, where the great cosmic web of matter would eventually stretch across space. But for now, in these early moments, the waves just traveled. They moved through the thickness, creating patterns, building structure, organizing the chaos of the early universe into something with rhythm and form. The cosmic bell rang on, its deep notes spreading farther and farther from wherever they started. Though starting point is a strange concept, when everywhere is the starting point. For hundreds of thousands of years, these vibrations continued. The universe kept expanding, kept cooling, but the sound waves kept traveling through it. The medium was still thick enough, still connected enough, for the pressure waves to move freely. But that was about to change, in a way that would freeze these ancient sounds into something completely different. These early vibrations weren't random chaos. They created patterns. Beautiful, mathematical patterns that spread through the universe in ways we can still detect today. Think of it like ripples in a pond again, but imagine those ripples in 3 dimensions, spreading outward in spheres rather than circles, all overlapping and creating interference patterns where they meet. Where 2 wave peaks met, they amplified each other, creating regions of even higher compression. Where a peak met a valley, they cancelled out, leaving calmer regions. This interaction created a complex web of density differences throughout the early universe, like an invisible blueprint stamped into the cosmic material. The strongest patterns came from the fundamental frequencies, the deepest notes in the cosmic symphony. These were the waves with the longest wavelengths, stretching across the largest distances. They compressed and expanded the biggest volumes of space, creating the large-scale structure that would shape everything to come. But there were also smaller patterns nested within the larger ones, shorter wavelengths, creating tighter ripples, medium-length waves filling the space between, all of them traveling at the same speed through the thick cosmic soup, all of them leaving their mark on the distribution of matter. It was like looking at a pond disturbed by multiple stones thrown at once, except in 3 dimensions and across the entire universe. These patterns mattered more than you might think. Where the sound waves compressed matter repeatedly, gravity had more material to work with. Those regions would eventually collapse in on themselves, forming the first structures in the universe. Where the waves spread matter thin, less would gather. The cosmic sound was literally composing the arrangement of everything that would come later. In the densest regions, marked by the convergence of compression waves, the first stars would eventually ignite. Around those stars, planets would form. In those regions, galaxies would gather. The pattern of sound waves from the universe's first moments was writing the story of where life could potentially exist billions of years later. Scientists call this the acoustic oscillation of the early universe. Acoustic just means sound. Oscillation means vibrating back and forth. It's a fancy way of saying the universe was ringing with sound waves that created patterns in how matter spread out. Those patterns became the seeds for everything we see today. The remarkable thing is how organized it all was. Despite the incredible violence of the Big Bang, despite the extreme conditions, the sound waves followed predictable physics. They created regular patterns, harmonious patterns. The universe wasn't born in chaos. It was born singing a song with structure and rhythm and repeating themes. But this singing couldn't last forever. The universe kept expanding, kept cooling, and as it did, the thick cosmic soup that carried these sound waves so perfectly was about to change in a fundamental way. The medium was thinning, the particles were spreading apart, and when they spread far enough, the sound waves would suddenly have nowhere left to travel, leaving their patterns frozen in a completely unexpected form. As the universe expanded, something inevitable happened. The thick cosmic soup that carried sound so well started thinning out. Imagine stirring water into paint. At first, the paint is thick and viscous, but as you add more water, it becomes thinner, more diluted, until eventually it's mostly water with just a hint of color. The universe did something similar, except instead of adding water, space itself was stretching, pulling everything apart. The particles that had been packed tight were now spreading farther from each other. The waves that could once push easily from one particle to the next now had longer distances to travel. Sound was still moving, but it was getting weaker. The medium was losing its grip. By the time the universe was about 380,000 years old, something critical happened. The temperature had dropped enough that electrons could finally settle into stable orbits around atomic nuclei. For the first time, complete atoms formed, and when that happened, the universe became transparent. Light could suddenly travel freely, without constantly bumping into free electrons. This moment is called recombination, and it changed everything. But here's what matters for our sound story. When atoms formed, the cosmic material stopped being a thick soup and became more like a thin gas. The sound waves that had been traveling so powerfully through the dense medium suddenly found themselves with almost nothing to push through. Like a speaker playing into a vacuum, the vibrations had nowhere left to go. The sound didn't disappear exactly. It just stopped traveling. Think of it like this. You're pushing a shopping cart across a smooth floor, and suddenly the floor becomes sand. The cart doesn't vanish. It just stops rolling. The energy you put into pushing it gets absorbed by the sand. The cosmic sound waves did something similar. They stopped propagating through space because the medium had changed too much. But where did all that wave energy go? Sound is energy, after all. Pressure waves moving through matter carry tremendous force. When those waves stopped being able to travel, that energy had to go somewhere. And it went into the very structure of matter itself, into the temperature variations and density differences that existed at that moment. This was like taking a photograph of the sound. At the instant when atoms formed and the universe became transparent, the pattern of compression and expansion from the sound waves got frozen into the distribution of matter and energy. Where a sound wave had compressed things, the matter was slightly denser and slightly hotter. Where it had expanded things, slightly less dense and slightly cooler. The cosmic song stopped playing, but its final note was preserved. From that moment forward, the universe became much quieter. Not silent, because vibrations still happened in the thin gas between galaxies, but nothing like the roaring symphony of the early universe. The age of cosmic sound had ended. Space became the mostly silent void we know today, where sound can barely travel at all. But those frozen patterns remained, stamped into the fabric of space, preserved in the oldest light in the universe. And billions of years later, humans would figure out how to read those patterns, to decode the fossil record of the universe's first song. When the universe became transparent at 380,000 years old, something extraordinary happened. Light that had been trapped, constantly bouncing between particles, suddenly broke free. Photons that had been stuck in the cosmic traffic jam for hundreds of thousands of years were suddenly released to travel through space unimpeded. And they're still traveling today. This light is called the cosmic microwave background, and it's the oldest light in the universe. It's been journeying through space for nearly 14 billion years, carrying information from that ancient moment when atoms first formed. Every direction you look in the sky, this light is arriving. It's everywhere, surrounding us, passing through us, a constant whisper from the universe's childhood. But here's the amazing part. This light isn't perfectly uniform. It has tiny temperature variations across it. Some spots are slightly warmer than others by just a fraction of a degree. These variations are incredibly small, differences of only about 1 part in 100,000. But they're there, and they matter tremendously. Those temperature variations are the sound waves, or rather, they're the fingerprint of the sound waves. Remember how the acoustic vibrations created regions of compression and expansion? Where matter was compressed, it was slightly hotter. where it was expanded, slightly cooler. When light finally escaped, it carried this temperature pattern with it. The hot spots and cool spots in the cosmic microwave background are literally showing us where the sound waves had compressed or expanded the universe at that moment. Think of it like pressing your hand into clay. When you pull your hand away, the clay keeps the impression of your fingers. The sound waves pressed their pattern into the matter and energy of the early universe, and when light escaped, it carried that impression outward. We're seeing the handprint of cosmic sound preserved in ancient light. Scientists can map these temperature variations across the entire sky. When they do, they see patterns, spots of warmth and coolness arranged in ways that aren't random. The patterns follow mathematical rules, the same rules that govern sound waves moving through a medium. It's like looking at a frozen pond and being able to tell where stones were thrown based on the ripple patterns locked in the ice. The largest warm and cool spots correspond to the deepest sounds, the fundamental frequencies with the longest wavelengths. Smaller spots show the higher harmonics, the overtones of the cosmic symphony. By measuring the size and distribution of these spots, scientists can work backward to figure out exactly what frequencies were present in the early universe. They can reconstruct the cosmic song from its frozen echo in light. This is genuinely remarkable when you pause to think about it. Sound waves that stopped traveling 13.8 billion years ago left their signature in light that's been journeying through space ever since. The universe kept a perfect record of its acoustic past, encoded in the oldest electromagnetic radiation we can detect. It's like finding a recording of a concert from before anyone invented recording devices, preserved by accident in the structure of the concert hall itself. And once scientists understood what they were looking at, they realized they could do something incredible. They could take those patterns and translate them back into sound, letting human ears finally hear what the universe sounded like at the beginning of time. Scientists faced an interesting challenge. They had the patterns from the cosmic microwave background. They understood these patterns represented sound waves from the early universe. But those sound waves had frequencies far too low for human ears to detect. The wavelengths stretched across vast distances, and the oscillations happened over timescales of thousands of years. No human could naturally hear them. So they did something clever. They sped up the frequencies. Think of it like taking a recording of someone speaking and playing it faster. The words are the same, the patterns are the same, but now they fit into a range we can actually hear. Scientists took the acoustic patterns from the early universe and compressed them in time, raising their pitch until they fell within the range of human hearing. The result is both eerie and beautiful. When you listen to the sound of the early universe, it's a deep hum with fluctuations. It rises and falls in pitch as different frequencies overlap and interfere. There are harmonics layered on top of each other, creating a chord that shifts and evolves. It sounds almost musical, which makes sense because music is just organized sound, and these cosmic vibrations followed very organized physical laws. The fundamental tone, the deepest note, represents the largest scale vibrations. These were compression waves that pulsed across enormous regions of space, creating the large-scale structure that would eventually become superclusters of galaxies. When you hear this bass frequency, you're listening to the rhythm that organized matter on the grandest scales imaginable. Layered on top are the overtones. These represent smaller vibrations, tighter patterns that created structure on smaller scales. Some correspond to what would become individual galaxy clusters. Others to the distribution within those clusters. Each frequency tells part of the story, and together they create a complex acoustic signature that carries an enormous amount of information. What's remarkable is that by analyzing which frequencies are present and how strong they are, scientists can learn about conditions in the early universe. The exact pitch of the fundamental tone tells us about the total density of matter. The strength of different overtones reveals the balance between ordinary matter and dark matter. The overall pattern confirms our understanding of how the universe has been expanding and evolving. This isn't just a fun curiosity, it's a legitimate scientific tool. The cosmic microwave background and its acoustic patterns are some of the most important evidence we have about the universe's history and composition. By listening to this ancient sound, translated into a form we can perceive, we're literally hearing the story of creation encoded in pressure waves. And every time someone plays this sound, they're experiencing something profound. Those vibrations, carried across 13.8 billion years of space and time. They influenced where galaxies formed, where stars ignited, where planets gathered. In a very real sense, those ancient sound waves had a hand in creating the conditions that led to Earth existing, to life emerging, to you being here right now, to listen to their echo. The sound that takes 14 billion years to hear is finally reaching human ears, not through the journey of the sound itself, but through the patterns it left behind in the oldest light we can detect. This ancient sound isn't just beautiful, it's meaningful. Every tone, every fluctuation, every harmonic carries specific information about the universe when it was just 380,000 years old. It's like a time capsule, but instead of objects, it contains data encoded in the pattern of vibrations. The deeper tones, the lower frequencies, point to regions where matter was compressed more strongly. These were the areas where gravity was already starting to win, pulling material together more tightly. Billions of years later, these regions would become the densest parts of the universe. Galaxy clusters, superclusters, the great filaments of the cosmic web, where matter gathered in long strands across space. The higher pitches tell us about smaller scale variations. These correspond to the seeds of individual galaxies and smaller structures. Where you hear a rise in pitch, that's a region that was slightly denser than average. Where the tone dips lower, that's a region that was slightly emptier. The universe at 380,000 years old was already showing the pattern of where it would build its largest structures. But there's more. The relative strength of different frequencies tells us about what the universe is made of. The fundamental tone's volume, compared to the overtones, reveals the balance between different types of matter. Scientists can measure how much ordinary matter was present, the stuff that makes up stars and planets and people. They can determine how much dark matter existed, the mysterious substance that doesn't interact with light, but pulls on everything with its gravity. The pattern also reveals the geometry of space itself. Sound waves of different wavelengths should arrive at different strengths, depending on whether the universe is flat, curved inward like a sphere, or curved outward like a saddle. By analyzing which frequencies are strongest, scientists determined that space is remarkably flat on large scales. The universe isn't wrapping around on itself. It extends outward in straight lines as far as we can measure. Even the slight variations in tone, the subtle shifts in pitch, tell us how fast the universe was expanding at that early moment. They confirm that expansion was smoothing out the initial irregularities, stretching the acoustic patterns across growing distances. The Doppler effect from this expansion slightly shifts the frequencies, and scientists can measure that shift to understand cosmic motion at the time. Think about what this means. A sound from nearly 14 billion years ago is giving us precise measurements of cosmic composition, geometry, and expansion rate. It's telling us what percentage of the universe is ordinary matter, around 5%. What percentage is dark matter, about 27%. What percentage is dark energy, roughly 68%. All from analyzing the harmonics of an ancient vibration. The accuracy is stunning. By studying these acoustic patterns, scientists have measured cosmic parameters to within a few percent uncertainty. That's like being able to weigh the entire visible universe and getting an answer accurate to within a few percentage points. All because sound waves in the early universe left their signature in observable light. Every note carries history. Every fluctuation preserves information. The cosmic hum isn't just something interesting to listen to. It's a scientific treasure, a message from the beginning of time that tells us exactly how the universe was built and what it's made of. Let's follow one imaginary sound wave from the very beginning. A single compression wave born in the intense heat of the early universe, traveling through time and transformation, eventually reaching us as information we can decode. This is its story. Our wave begins when the universe is impossibly young, just fractions of a second old. It starts as a tiny fluctuation in density, a region where matter and energy happen to be packed slightly tighter than the surroundings. Gravity pulls inward, pressure pushes outward. The battle between these forces creates a pulse that spreads in all directions. The wave moves fast through the thick cosmic soup, traveling at about half the speed of light. As it goes, it compresses matter ahead of it, creating a peak. Behind it, matter spreads thinner, creating a valley. The wave oscillates, pulsing between compression and expansion, carrying its pattern outward through the dense material. For thousands of years, our wave travels like this. The universe is still opaque, still thick enough for sound to move freely. The wave passes through regions that will someday become galaxy clusters. But right now, they're just slightly different densities in the cosmic fog. It encounters other waves, sometimes adding together to become stronger, sometimes cancelling out to become weaker. As time passes, the universe keeps expanding. Our wave's wavelength stretches along with space itself. What started as a compression wave with a certain size is now longer. Its peaks and valleys spread across greater distances. The wave is being pulled apart by the expansion of the universe, but it's still traveling, still oscillating. Then comes the critical moment. At 380,000 years, atoms form. The cosmic soup transforms into transparent gas. Our sound wave suddenly has nowhere left to travel. The medium that carried it so well has thinned too much. The wave stops propagating, its energy absorbed into the structure of matter at that exact moment. Where our wave had compressed matter, that region is now slightly warmer and slightly denser than average. Where it had created valleys of expansion, those regions are slightly cooler and less dense. The wave has effectively frozen its pattern into the distribution of matter and energy. It's no longer moving, but its influence remains, stamped into reality. Light that was trapped for those first 380,000 years now escapes from this region. The photons carry with them the temperature variations our sound wave created. They begin their own journey through space, traveling at light speed, carrying the fingerprint of our ancient acoustic pulse. For nearly 14 billion years, those photons travel. They pass through empty space, around forming galaxies, across the expanding universe. The wavelength of the light itself stretches as space expands, shifting from visible light to infrared to microwave radiation. But the pattern remains. The slight temperature difference our sound wave created is still encoded in those photons. Finally, those photons reach Earth. Telescopes detect them. Scientists measure their temperature, and there, in the data, is the signature of our wave. One small contribution to the overall pattern of the cosmic microwave background. Our sound wave, born in the universe's first moments, has finally delivered its message. Not as sound anymore, but as information preserved in light that's been traveling for most of cosmic history. To truly understand this cosmic sound, we need to grasp just how incredibly deep it is. Not deep like a bass drum or a whale's call. Deep on a scale that makes those sounds seem high-pitched by comparison. The wavelengths of the fundamental cosmic tones stretched across distances that challenge comprehension. In the early universe, the longest acoustic waves had wavelengths measuring hundreds of thousands of light years. Think about that. One complete cycle of the wave, from compression to expansion and back to compression, covered a distance that light would take hundreds of thousands of years to cross. These weren't sounds in any conventional sense. They were cosmic-scale pressure variations pulsing through the fabric of space. If you could somehow have been there to experience these waves in their natural form, with ears capable of detecting such low frequencies, one vibration would take millions of years to complete. You'd feel the compression phase for eons, as matter around you slowly pressed inward. Then, just as slowly, the expansion phase would arrive, and everything would gradually spread apart. Then, compression again, a rhythm so slow it would outlast civilizations. Human hearing typically ranges from about 20 vibrations per second at the low end to 20,000 at the high end. The cosmic fundamental frequency was more like one vibration every few million years. That's not just outside our hearing range. It's in a completely different category of vibration, operating on timescales, geological rather than biological. Even today, if those waves still existed in their original form, we'd have no way to hear them naturally. They'd be pressing on us constantly, but so slowly that we'd never notice the change. Like trying to observe a mountain eroding. It's happening, but the timescale is too vast for direct perception. The compression and expansion would pass through us over generations without any sensation of sound. This is why translating the frequencies matters so much. By speeding them up tremendously, scientists compressed millions of years of vibration into seconds of sound. It's like watching a time-lapse video of a flower blooming. The process normally takes hours, but sped up, you can watch it unfold in moments. The cosmic sound works the same way. The pattern is preserved, just played at a speed our ears can actually process. The shorter wavelength patterns, the overtones, were smaller but still enormous by everyday standards. These might have wavelengths of thousands of light years instead of hundreds of thousands. Still far too low for human hearing. Still operating on timescales of thousands or tens of thousands of years per vibration, but smaller than the fundamental tone, creating tighter patterns in the cosmic structure. All of these frequencies together created a chord. Not a chord in the musical sense, with notes we'd recognize, but a combination of vibrations at different scales, all happening simultaneously. The universe wasn't humming a single note. It was playing multiple notes at once, each contributing to the overall acoustic landscape, each leaving its mark on the distribution of matter. Understanding this scale helps us appreciate what scientists accomplished. They took vibrations operating on timescales longer than human history and made them accessible to human ears. They translated the deepest possible sounds into something we can experience and learn from. The universe didn't stop making sounds after those first 380,000 years. Even though the thick cosmic soup thinned out and space became mostly silent, vibrations still happen. They're happening right now, all around us, in the vast spaces between stars and galaxies. The symphony continues, just in a quieter, more scattered way. Black holes create some of the most powerful acoustic events in the modern universe. When two black holes spiral together and merge, they don't just release gravitational waves. The event also sends pressure waves through any gas nearby. These ripples move through the thin material surrounding the black holes, creating sounds too low for human ears, but real nonetheless. One merger might create vibrations with wavelengths stretching across light years. Galaxy clusters, the largest gravitationally bound structures in the universe, also hum with low-frequency sound. Hot gas trapped between galaxies in these clusters can vibrate. Supermassive black holes at the centers of galaxies pump energy into this gas, creating pressure, waves that travel outward. Scientists have detected these vibrations in several galaxy clusters, finding notes that, if translated to human hearing range, would sound like deep rumbles. In one famous case, a galaxy cluster called Perseus has a black hole creating sound waves with a wavelength of about 30,000 light years. The note is a B flat, but 57 octaves below the lowest note a piano can play. That's the deepest note ever detected from any object in the universe. It's been playing for billions of years, a cosmic drone echoing through the hot gas of the cluster. Stars themselves ring like bells. Our sun vibrates with millions of different frequencies as pressure waves bounce around inside it. These vibrations make the sun's surface rise and fall by tiny amounts. By studying these oscillations, scientists can learn about the sun's interior structure, using sound as a probe to see inside a star. Other stars do the same thing, each with its own unique acoustic signature. Exploding stars create massive shockwaves that travel through surrounding space. When a supernova occurs, it doesn't just release light, it creates an expanding shell of material that plows through nearby gas, compressing it, creating pressure waves that spread across light years. These cosmic explosions are some of the loudest events in the modern universe, though loud is relative when there's barely any medium to carry the sound. Even the spaces between galaxies aren't completely empty. Thin filaments of gas connect galaxy clusters in a vast cosmic web. Occasionally, galaxies moving through these filaments create bow shocks, like a boat moving through water. These shocks are pressure waves traveling through the intergalactic medium, another form of cosmic sound operating on enormous scales. The universe is full of vibrations if you know how to look for them. They're not the organized, powerful acoustic waves of the early universe. They're more scattered, isolated events. But they're there, proof that sound never completely left the cosmos. It just became quieter, more subtle, harder to detect. The symphony continues playing, even if most of its instruments are now silent, leaving just occasional notes ringing through the darkness. Detecting cosmic sounds requires some of the most sensitive instruments humans have ever built. We can't hear these vibrations naturally, so we've created tools that can sense what our ears cannot. These tools don't listen in the traditional sense. Instead, they observe the effects that sound waves leave behind. For the ancient cosmic sound, scientists use specialized telescopes that detect microwave radiation. These aren't optical telescopes that capture visible light. They're designed to pick up much longer wavelengths, the kind of light that the cosmic microwave background emits. Satellites orbiting Earth scan the entire sky, measuring the temperature of this ancient radiation in every direction with incredible precision. The most famous of these satellites was called Planck. It operated from 2009 to 2013, mapping the cosmic microwave background with unprecedented detail. It could detect temperature differences as small as a few millionths of a degree. This sensitivity allowed scientists to see the acoustic patterns left by sound waves in the early universe with stunning clarity. The data from Planck has given us our most detailed picture of the cosmos at 380,000 years old. But measuring temperature variations is just the first step. Scientists then have to analyze those measurements, looking for patterns that match what sound waves would create. They use complex mathematics to transform the temperature map into frequency information, essentially converting a picture into sound. This process reveals which acoustic frequencies were present and how strong they were. For modern cosmic sounds, like those from galaxy clusters, scientists use X-ray telescopes. Hot gas emits X-rays, and when that gas vibrates from sound waves, the X-rays show ripples and patterns. By studying these X-ray images carefully, scientists can detect the compression and expansion zones created by acoustic waves traveling through the thin intergalactic medium. It's like watching ripples on a pond, except the pond is millions of light years across, and the ripples are in X-ray emitting gas. Some cosmic sounds are detected through radio telescopes. These massive dishes pick up radio waves emitted by various objects in space. When gas clouds vibrate, they can emit radio waves with patterns that reveal the presence of sound waves moving through them. Radio astronomy has opened a window into acoustic phenomena we couldn't observe any other way. For sounds inside stars, scientists use a technique called helioseismology when studying the Sun, or asteroseismology for other stars. They measure tiny brightness changes caused by the star's surface moving up and down as sound waves bounce around inside. These measurements are incredibly precise, detecting motion of just a few meters on a star millions of kilometers wide. But that precision allows scientists to map the interior of stars using sound, much like ultrasound maps the inside of a human body. Gravitational wave detectors like LIGO can sense ripples in space-time itself. While gravitational waves aren't sound in the traditional sense, they do share similarities with acoustic waves. Both are vibrations traveling through a medium, and both carry information about the events that created them. LIGO has detected dozens of black hole mergers, each one creating gravitational ripples that complement the acoustic effects happening in nearby gas. All these instruments work together to reveal the hidden acoustic landscape of the universe, letting us hear what our ears alone never could. Those ancient sound patterns did more than just exist. They shaped reality in ways that echo all the way to this moment, to you reading these words, to every breath you take. The connection between cosmic acoustics and your existence is direct and profound. Remember how the sound waves created regions of higher and lower density in the early universe. Those weren't just temporary patterns. They became permanent features once the waves stopped traveling. The compressed regions had more matter to work with. The expanded regions had less. And gravity is patient. It had billions of years to work with these density differences. Where matter was denser, gravity pulled harder. More material gathered. These regions began to collapse in on themselves, slowly at first, then faster as more matter accumulated. Over millions of years, the densest spots became the seeds of galaxy clusters. Slightly less dense spots became individual galaxies. Even less dense regions became the voids between galaxies, the empty spaces in the cosmic web. The galaxy you're in right now, the Milky Way, formed in one of these regions. Billions of years ago, the matter that would become our galaxy was pulled together by gravity, gathering in a spot that was slightly denser than average, because a sound wave compressed it when the universe was young. Without that acoustic compression, the matter might have been distributed differently. Our galaxy might never have formed where it did, or how it did, or perhaps at all. Inside that gathering cloud of matter, smaller density variations created more structure. The galaxy didn't form as one smooth blob. It developed spiral arms, a central bulge, regions where star formation happened more readily. These structures also trace back to the patterns created by sound in the early universe, smaller scales of the same acoustic blueprint. In one region of our galaxy, about 5 billion years ago, a particular cloud of gas and dust began to collapse. This cloud was enriched with heavy elements from previous generations of stars, elements that wouldn't exist without the specific chain of events leading back to how matter was distributed. The cloud spun and flattened into a disk. At the center, the sun ignited. Around it, planets began to form from the remaining material. One of those planets formed in what scientists call the habitable zone, where temperatures allow liquid water to exist. That planet was Earth, and Earth had the right ingredients, the right distance from the sun, the right size, the right conditions for something remarkable to emerge. Life. Single cells at first, then complex organisms, then consciousness, then you. Every atom in your body was forged in stars that formed in galaxies that gathered in regions compressed by sound waves 13.8 billion years ago. The oxygen you breathe, the carbon in your cells, the iron in your blood, all of it traces back through a chain of causation to those ancient acoustic vibrations. If the cosmic sound had been slightly different, if the frequencies had been stronger or weaker, if the pattern had varied in certain ways, the universe might have evolved differently. Galaxies might have formed at different times or places. Stars might have had different compositions. Earth might never have existed. You are, in a very literal sense, the result of cosmic music. The universe sang itself into structure, and that structure eventually produced stars, planets, and life. There's something mind-bending about detecting this ancient sound. When scientists measure the cosmic microwave background, they're not seeing the universe as it is now. They're seeing it as it was nearly 14 billion years ago. Time and distance become the same thing when you're looking across the cosmos. Light travels fast, but space is vast. The speed of light is about 300,000 kilometers per second, which sounds incredibly quick. And it is, by human standards. But when you're crossing billions of light years, even light takes time, a lot of time. The photons carrying information about the early universe's sound waves have been traveling for almost the entire age of the universe. Think about what that means. Those photons left their origin point when the universe was 380,000 years old. They've been moving through space ever since, covering unimaginable distances. While they traveled, stars formed and died. Galaxies collided and merged. Planets appeared and evolved. On one particular planet, life emerged, evolved intelligence, developed technology, and built telescopes capable of detecting those ancient photons just as they arrived. Every second of their journey represents about 300,000 kilometers of distance. Every minute, about 18 million kilometers. Every hour, over 1 billion kilometers. Every day, about 26 billion kilometers. Every year, nearly 10 trillion kilometers. And they've been traveling for nearly 14 billion years. The numbers become so large, they lose meaning, but the concept remains. These photons have crossed an almost incomprehensible gulf of space and time to reach us. When you look at the cosmic microwave background, you're looking backward through time. You're seeing the universe as it was in its infancy. The light itself is a time machine, carrying information across eons, preserving the state of reality from a moment long before anything familiar existed. But here's something even stranger. As those photons traveled, space itself was expanding. The distance between their starting point and Earth wasn't fixed. It was growing. The photons had to cover not just the original distance, but also all the new space that appeared as the universe expanded during their journey. In a sense, they were running on a treadmill that kept getting longer. This expansion stretched the photons themselves. Light that started in the visible range, the kind our eyes could see, got pulled to longer wavelengths. It shifted through infrared, then into the microwave range where we detect it today. The cosmic microwave background isn't microwave because it started that way. It's microwave because 14 billion years of expansion stretched it to those wavelengths. The acoustic patterns preserved in this light also got stretched. Compressions and expansions that existed on certain scales when the light was emitted now appear larger due to the universe's expansion. Scientists have to account for this stretching when they analyze the data, working backward to figure out what the original patterns looked like. So, when we detect this ancient sound, we're receiving a message that traveled for 14 billion years across expanding space, carrying information about vibrations that stopped propagating long before the journey even began. Time, distance, expansion, and preservation all combine to deliver this cosmic telegram directly to our instruments, letting us glimpse and hear something from the universe's distant past. For all we've learned about cosmic sound, there are still acoustic mysteries waiting to be solved. Vibrations we haven't detected yet. Sounds from moments even earlier than the cosmic microwave background can show us. The universe keeps some of its acoustic secrets hidden, at least for now. The cosmic microwave background shows us the universe at 380,000 years old, when atoms formed and light could finally travel freely. But what about before that? What sounds existed in the first moments, the first seconds, the first fractions of a second after the Big Bang? Those vibrations happened, governed by the same physics, but we can't see their direct signature in light because light was trapped during that time. Scientists think these earliest sound waves might have left traces in other ways. Gravitational waves, ripples in space-time itself, could carry information from the universe's first instant. These primordial gravitational waves would be incredibly faint, stretched by expansion just like light waves. Detecting them would require even more sensitive instruments than we currently have. But if we could measure them, they'd tell us about sound in the universe before anything we've observed so far. There are also theoretical structures called cosmic strings. If they exist, that would create specific patterns of sound in the early universe. These aren't strings like you'd tie things with, but mathematical objects, defects in the fabric of space left over from phase transitions when the universe cooled. If cosmic strings are real, they would have generated distinctive acoustic signatures. Scientists look for these patterns in the data, but so far, nothing conclusive has appeared. Dark matter remains another acoustic mystery. We know it exists because of its gravitational effects, but it doesn't interact with light. Sound waves in the early universe moved through both dark matter and ordinary matter, but in slightly different ways. The dark matter didn't feel pressure the same way ordinary matter did. It responded only to gravity. This created subtle differences in how acoustic patterns developed. We can see hints of this in the data, but dark matter itself remains silent and invisible, revealing itself only through its gravitational influence. Before stars formed, before any light sources existed, except the fading glow of the Big Bang itself, there was a period called the Cosmic Dark Ages. During this time, sound waves in the thin hydrogen gas probably still occurred, but we have no way to detect them yet. The hydrogen emitted a specific wavelength of radio waves that astronomers hope to detect someday. If they can, it would reveal acoustic activity from this mysterious era between the first light and the first stars. Even the nature of the Big Bang itself raises acoustic questions we can't fully answer. What caused the initial expansion? Was there sound in whatever existed before? If before even makes sense in that context. Did the first vibrations start from quantum fluctuations? Tiny, random variations amplified to cosmic scales? These questions push at the edges of physics, where our understanding becomes uncertain. The universe has given us remarkable access to its acoustic history, but it hasn't revealed everything. Some sounds remain beyond our current ability to detect, waiting for better instruments, new techniques, or different ways of thinking about cosmic vibrations. Let's return to the specific sound that started this journey. The vibration that took 14 billion years to reach us. This is the longest echo possible in our universe. A message from the cosmic beginning that's only now arriving at our detectors. After traveling through the entire history of everything, an echo, in the everyday sense, is sound bouncing off something and returning to you. You shout into a canyon, and seconds later, your voice comes back. The sound travels to the wall, reflects, and returns. Cosmic echoes work differently. There's no wall for sound to bounce off. Instead, the sound gets frozen into light, and that light travels across space for billions of years before reaching us. It's an echo through time rather than space. This particular echo carries information from when the universe was just beginning to settle into structures. Before that moment, everything was too hot and dense for distinct objects to exist. After that moment, matter began clumping together, forming the seeds of galaxies. The sound we detect captures that transitional instant, the moment between chaos and order, between formlessness and structure. The patience required is staggering. The vibrations stopped traveling at 380,000 years, frozen into the temperature patterns of the cosmic microwave background. Then, those patterns had to journey across expanding space for nearly 14 billion years. No rushing, no shortcuts, just photons moving at light speed through the growing universe, carrying their cargo of information across ions. During that journey, countless events occurred. Billions of galaxies formed, trillions of stars ignited, and many died. Planets without number appeared around those stars. On at least one planet, life emerged and eventually developed the ability to build instruments that could detect and decode this ancient message. All while the photons carrying the acoustic patterns continued their journey, oblivious to everything happening around them. The echo didn't weaken much during transit. Unlike sound traveling through air, which fades with distance as energy spreads out, these photons maintained their information remarkably well. Yes, expansion stretched their wavelengths, and yes, the density of photons decreased as space grew. But the pattern remained intact. The acoustic signature survived the journey almost perfectly. When we detect this echo now, we're receiving something that's been traveling for essentially the entire age of the universe. There is no older detectable signal. Nothing carries information from a more distant past. This is as far back as electromagnetic radiation can show us. The oldest light possible, carrying the oldest sound possible. It's the universe's most ancient message to us. Not sent deliberately, not encoded with intent, but preserved by the laws of physics and delivered across the longest timescale imaginable. The cosmos wasn't trying to communicate, but it created a record anyway, an accidental time capsule that tells us exactly what conditions were like at the moment of its creation. This echo will keep arriving for as long as we exist to detect it. The cosmic microwave background surrounds us completely. Everywhere we look, these ancient photons are coming in, carrying their 14 billion-year-old message about sound in the early universe. The echo plays continuously, a constant whisper from the beginning of time, reaching us now after the longest possible delay. There's something profound about being able to hear time. Not the ticking of a clock or the passage of seasons, but time on a cosmic scale. These ancient vibrations are frozen moments from the universe's childhood, now accessible to beings who appeared billions of years later. It's a kind of temporal archaeology, digging through layers of history, not with shovels, but with telescopes and mathematics. When scientists play the translated sound of the early universe, they're doing something humans have never been able to do before. We can read about history in books. We can see fossils from ancient life. We can study rocks that formed billions of years ago. But actually, hearing something from the universe's beginning, that's new. That's unprecedented. It connects us to deep time in a visceral way that numbers and images alone cannot. The sound itself is strange and beautiful. That deep hum with its fluctuations and harmonics. It doesn't sound like music because it wasn't designed to be musical. It's physics expressing itself through vibration. Yet, there's something almost musical about it anyway. The overtones layering on the fundamental frequency. The way different tones rise and fall. It's organized sound, even if the organization comes from natural laws rather than artistic intent. What strikes many people when they first hear it is how ordinary it seems in some ways. It's not alien or incomprehensible. It's just sound. Strange sound, yes. Ancient sound, certainly. But still recognizable as vibration with pitch and rhythm. The universe speaks a language we can understand, at least in this acoustic form. But the meaning behind the sound is anything but ordinary. Every fluctuation in pitch represents a region of space that would eventually become galaxy clusters or voids. Every harmonic corresponds to a scale of structure in the cosmos. When you hear the fundamental tone, you're hearing the largest structures being organized. When you hear the higher overtones, you're hearing the smaller patterns being set. The sound is a blueprint, an audio map of the universe's future structure. This achievement represents something remarkable about human curiosity and capability. We're tiny creatures on a small planet, orbiting an average star in an ordinary galaxy. Yet, we've managed to reach back through nearly 14 billion years of history to capture and decode information from the universe's infancy. We've turned patterns in ancient light into sound our ears can process. We've made the incomprehensibly old accessible to our brief existence. It's also humbling. These vibrations don't care about humanity. They existed long before us and would have continued existing whether we decoded them or not. The universe wasn't making sound for us to hear. It was just following the laws of physics. We're observers discovering something that happened regardless of our presence. Reading a record that wasn't written for anyone in particular. Yet, we are here. We did figure it out. And in doing so, we've connected ourselves to the deepest history possible. We've found a way to experience, even if only indirectly, what the universe was like when it was young. We've listened to time itself, hearing echoes from an era when nothing familiar existed. That connection, that act of listening across such vast stretches of time, is one of humanity's most beautiful achievements. And so we come back to where we started, back to this moment, back to you, settling into the quiet of your room, breathing slowly, feeling the weight of your body against whatever supports you. The cosmic journey has brought us full circle, from the ancient sound to this present instant, connecting vast scales of time and space to your immediate experience right now. The universe's hum continues, whether we listen or not. The cosmic microwave background keeps arriving from all directions. Those ancient photons, still carrying their 14-billion-year-old message about sound in the early universe. The echo plays on, constant and unchanging, a permanent feature of reality. It was there before humans existed. It will be there long after we're gone. But right now, in this moment, you know about it. You've traveled through the story of how sound shaped the cosmos, how vibrations from the beginning influenced everything that came after, how those ancient patterns eventually led to your existence. You're connected to that history now, aware of your place in the chain of events stretching back to the universe's first moments. The sound that took 14 billion years to hear has finally reached not just our instruments, but our understanding. We've decoded it, translated it, made it accessible to human perception. What was once incomprehensibly distant and ancient has become something we can experience, learn from, and marvel at. The gulf between then and now, between there and here, has been bridged through curiosity and science. As you lie there, remember that you're made of atoms, forged in stars that formed in galaxies, shaped by those ancient sound waves. The oxygen moving through your lungs, the carbon in your cells, the calcium in your bones. All of it connects back to the cosmic acoustics we've explored tonight. You are, quite literally, part of the song the universe sang to itself billions of years ago. The patterns from those vibrations are still visible in the structure of the cosmos. When you look at the night sky, the arrangement of stars and galaxies carries the fingerprint of acoustic waves from the early universe. The cosmic web, the clusters and voids, the distribution of matter across space. All of it shaped by sound that stopped traveling before Earth existed. And somehow, improbably, wonderfully, a species evolved on one small planet that could figure all this out, that could build instruments sensitive enough to detect ancient light, mathematics powerful enough to decode its patterns, and imagination vast enough to understand what it all means. We found a way to hear the unhearable, to see the invisible, to know the unknowable. If you've enjoyed this journey through cosmic sound, and these quiet explorations of science bring you peace or spark your curiosity, click that like button and consider subscribing so you don't miss where we wander next. Maybe you'll join us as we drift through the strange physics of black holes, or float among the possibilities of other universes, or discover what happens at the quantum edge of reality. There are so many beautiful mysteries still waiting. For now, let yourself rest. Let the weight of 14 billion years settle gently around you, not as a burden, but as a comfort.